So students, hello and welcome to the third part on the embedded system design verification and test course, and we are dealing with embedded system testing. So as we are dealing with the advanced part of testing as of now, so in the last lecture we have covered a part of concurrent testing for fault tolerance on embedded system. That is, after looking at the advanced fault models and built-in self-test, then we started looking at why online testing or concurrent testing is very much required in modern embedded systems, because modern embedded systems, as you know, are very much required in all mission critical applications like avionics, cruise control, etc. So if any fault happens before the startup of the device, then we can detect by BIST. And if it is in a manufacturing defect, then we can do a test by an ATE before the chip is shipped to the market. But if anything problem happens while it is in operation, then there is only one way to detect it, which is called online testing or concurrent testing, and that is very much required for fault tolerance. And we discussed in last lecture that we will be giving 2 lectures on this, and already the third one we have covered in the last class. Today we are going to look at the second part of that online testing business. So what we had basically seen that mainly when you are going to get online tests, there are several schemes like signature monitoring in finite state machines, and then mainly we looked at one major emphasized on basically something called self-checking design, in which case the inputs and the outputs are all coded using some error detecting codes. And then in the output we have to find out whether if there is some error or fault in the circuit, then the output will not be belonging to that particular code word. Like if you have a even parity, so if there is a fault, the output will be an odd parity and so forth. But then we have found out that parity is not a very good way of handling online test mechanism, because parity is basically checks 1 bit error, or if you have odd number of errors basically in the output. But main problem is that we have seen that if there is even number of errors or bidirectional errors, like bidirectional means 0 to 1 line will be from 1 to 0 to 1 and 1 will be from 1 to 0, or if the even number of bits get changed, then parity cannot do anything. Then we looked at something called unidirectional codes, that is amount of n codes or Berger codes. Then they have slightly more power than your basically your parity bit error detection code, because they can detect multiple bits. Even odd number of bit errors are possible to be detected by this unidirectional codes, but of course then the error should be unidirectional, that is either all bits become 0 to 1 or 1 to 0. So basically what we have seen that single stacked faults in the circuit can be detected if such a fault results in either a single bit error. Single bit error is very easy to detect, basically by any parity mechanism it will be detected, or unidirectional multi-bit errors at the outputs. So unidirectional means, again I am emphasizing that if the errors are all from 0 to 1 or 1 to 0, then it is easy to detect. Extremely difficult cases happen if they are bidirectional errors, that is one goes from 1 to 0 and the other line goes from 0 to 1. That actually balances the errors. So in fact it is very difficult to detect such errors, and extremely complicated coding may be used to do it, but then the tested area will also become very high. Here one thing is very important to understand, that I can do online testing and I can go for even detecting multidirectional errors, bidirectional errors, everything I can do. But if for a circuit of size x I am putting another circuit of size 10x or something to detect the errors online, then it is not a very good attitude. It is like something like killing a mosquito with a cannon. You have a circuit whose size is x, you have to use slightly smaller circuit, or at least with a much lower area than x, which can detect online errors in that. Basically the idea is that if you have one circuit under test of x area and you have the tester whose circuit area is small, then I already told you in the last class, then probability of errors occurring in that smaller circuit is lower than the larger circuit. Because in case of online test or in built-in self-test, both the circuit as well as the tester are on chip. So same chip, basically both of them are there. It is not like an offline test where an ATE is there and the tester actually tests the chip. But in this case, both the circuit as well as the tester are on the same chip. So faults can happen either in the circuit or in the tester itself. So tester has to be very carefully built, so it should be of a smaller area compared to the cart. So then you can assume that the probability of faults occurring in the testers are less. So we have to always try to keep the tester area small. So basically that is why if you are thinking about multidirectional errors, it is extremely difficult. Codes are available, a lot of modification in the circuits are required to detect such errors, and it may require the circuit tester area to become very high. So when we talk about online testing, we are very much scared about something what is called as a bidirectional errors. So what we have learned in the last class, that single stacked faults, if they result in a single bit output error or multiple bit unidirectional errors, then there are a lot of codes available to detect it, and the circuit area requirement for designing the testers are also very less. So one important one is parity, but as again discussed, parity can detect only single bit or odd number of bit errors. But slightly advanced are basically you already seen unordered code basically. Again I am just giving a repetition of yesterday's lecture because we will start continuing from this point. So as a recap, we have seen there is something on unordered code. Unordered codes are something like one should not cover the another. That is basically if you look at it, so in this point this is a 1 and this is a 0, but another in this point, 1 minute. So basically the idea of unordered code is something like this one. That is this one will have a 0 and this is a 1 at this point. So this one is going to cover this, and in this case this one is going to cover this. So nobody is going to cover each other. So therefore in this case basically they are actually called unordered codes. Neither x covers y, not y covers x. So we have seen that basically the formal proof, although we have not discussed basically, but unordered codes can be used to detect multiple bits unidirectional errors. The proofs exist. One thing at this point I would like to tell you is this coding theory was basically used or massively used in engineering discipline for some other purpose, that is a communication error. So whenever you are communicating some burst of bits over a medium like wired medium, or more importantly a wireless medium, so maybe you are transmitting a packet where there is a header, this is a network packet, there is a footer and lot of 0, 1, 1, 0, 1 some bits you are transmitting, and you are transmitting over the medium, maybe a air, it is a wireless communication. Due to lightning etc., what happens basically, some of the bits get flipped. So say the bits are flipping through the air, and then there is a lot of lightning or some disturbances happen. Then what happens, the lot of bit get flipped to one direction. So what happens basically, let us assume that the numbers or something like this is going as a lightning. So everybody is pulled to 1. So what happens, this one will also become 1, this one will also become 1, and all other bits will be 1 because of this closed coherence nature. So if some data is flowing from one part to another over the wave, and there is a lightning or noise which comes, then they try to flip the bits in one direction, because it is not because of an error as in the circuit. In the circuit what happens, the error is a stacked fault or some fault in a gate which gets reflected in the output, in some case of bits getting flipped from 0 to 1 or 1 to 0. But coding theory was mainly used for detecting errors in the communication channel. Communication channel, the errors does not happen because of faults in the wires or something. It basically happens because of interference or some lightning or external noise. In such cases what happens, basically all the bits try to get biased by the neighbors or by the noise, and they try to go in one direction. In other words, to keep the long story short, errors in communication channels are generally unidirectional. That is, all becomes 0 to 1 or all becomes 1 to 0 based on the influence of the neighbors or based on the lightning effect or some other fault or interference. But that phenomena is not true for circuits, because circuit you have one point, there is a stacked fault, and it can reflect obviously in multidirectional errors at the output. That is why this coding theory basically are widely used for online testing, but still it is not a very good match basically for online tests, because it results in multidirectional errors in circuits. But from where the branch of engineering from where the motivation has been borrowed is communication channels. There the probability of occurring of multidirectional errors are less, as I have explained. Detailed theory you can read any communication textbook and it will be clear, right? And also in that case the error detecting hardware is present at one part of the channel. So for example, this is the transmitter and this is the receiver. In the receiver end of the channel, you will have a error detecting hardware. So in this case, there is no limitation in the area of the hardware. You can use an extremely complicated coding theory and you have a hardware box to test it. Test that whether the transmission was proper or not. Because the communication channel which you are considering as the device under test and the tester are two separate entities and they are not in a single point. But in case of circuits, the challenge is much higher, because the circuit as well as the tester are on chip. So you cannot use a very complicated coding theory to do that. So therefore again I am repeating, in case of online testing, bidirectional errors are basically nightmares. So we cannot use a very complicated code to do it. So people try to handle it in a different manner as we will look in this course. But what people do, many people assume that I will only detect unidirectional errors, bidirectional errors I will forget, because basically that will make my tester very difficult. And as already I told you, most rigorous testing is done after design and manufacturing, then BIST is slightly lower, online testing is further lower, because in online testing you cannot test as rigorously as the manufacturing test in a AT. Then if you do that, your tester will become much larger than your circuit itself. So this is a pyramidal structure basically. So therefore I have to compromise many things in online testing. So many people tell that we will design a tester but it will only detect unidirectional errors. So use a simple coding theory to do that. So basically what was the motivation? So basically one error will be converting from 1 to 0 and the other will be from 0 to 1, but there cannot be in a mix. This either all bits will be from 1 to 0 or all bits will be changing from 0 to 1. So that is actually a unordered code. Now I am not going into the exact proof, because as I told you, this coding theory has come from communication, and a lot of theory proofs are there why it will work. There are already proof guarantees are there. The proof guarantee says that if there are unidirectional errors, unordered codes can detect it. The formal proof you can read it, but we are not going to bring it in the testing VLSI test or embedded system perspective, because again I am repeating, we just take the proofs and we just use this concept for testing. But slightly some idea I will give you. Very important coding unidirectional codes are m out of n codes, already we have used, and basically Berger code. So Berger codes basically m out of n codes means exactly m number of ones and m minus s number of zeros. The Berger code basically you have a information part, the number of zeros are counted and you put a binary count for that. In this case there are 4 zeros, 1, 2, 3, 4 and 3 ones. So C is the coding part, that is we will be representing the number 4 because there are 4 number of zeros. So now you can very easily appreciate the fact, as I will show you, that if there are unidirectional errors, they can be very easily detected. Like for example, I am taking a hot 1 coding, 1 out of n code. So let me say that is the number, sorry, there will be only 1 0 0 1 dot dot dot. So these are the only codes possible. I am taking m equal to 1, that is only 1 once in the entire binary vector. Now I can tell you, very easily you can appreciate that if there are unidirectional errors, what is going to happen? Unidirectional happen means the 2 zeros will become 1, or 1 0 can become a 1, but you cannot have this 0 becoming 1 and this 1, you cannot have two different ways, like this 1, this 0 becoming 1 and this 1 becoming 0, that cannot happen basically. But be careful that if it happens, the error cannot be detected, like 1 is a coding like this, sorry. So this is one code like 1 0 0 0 0. So if it's a bidirectional error, this one is going to become a 1 and this is going to become a 0. So in this case, this is another the error vector, but still this follows the hot 1 encoding. But unidirectional assumption of non-unidirectional errors prohibits this. That we are assuming that such errors are not going to happen, which will change 1 bit from 0 to 1 and 1 bit from 1 to 0. That we are not allowing. So if it is not allowed, then you can very easily appreciate the fact that either this one will become a 1 or this or both of them or this one. So it will obviously change the number of ones. It will no longer remain a hot 1 encoding. So if there is any unidirectional error which moves from this one to this one, then it will change the number of ones, which will no longer remain a single one. So error will be easily detected. Other way, even if the other way unidirectional error happen, like for example this one will become 0, then the number of ones will be 0, which is also not possible in the hot 1 encoding. So in fact, you can easily try with 2 ones. The idea is very simple. If you are using 2 1 encoding, so in this case if you see that 1 1 then 0 0 0, then it will be again 0 0, maybe 1 1 0. These are the codes. You can easily appreciate the fact any type of unidirectional error will change the number of ones, and as the number of ones are fixed in the encoding, very easily you can detect. But if there is a bidirectional error, then actually there can be error balancing. The main problem of bidirectional error is error balancing, bit number balancing, like sorry. So this one will change to 1 and this one will change to 0. So again the number of ones remain 2. So errors are easily balanced. So bidirectional errors are basically very nightmare for online testing. Now we will see what people have tried to avoid. Some people, as I told you, assumes that if there is a bidirectional error, we are not going to detect it. Simply the fault coverage will come down, but still whatever is possible to do with unidirectional unordered codes, detect all faults leading to unidirectional errors will only be detected. If some fault results in a bidirectional error, it will not be detected. Bring down the fault coverage. We cannot do anything because we want to keep the tester area low. There is one group of people actually work by this mechanism, but there are a lot of scientists who try to avoid bidirectional errors, which we will see in a very short while from now. Similarly, as a homework, you can also try to find out that in the Berger code also, if there is a bidirectional error, so if there is a unidirectional error, you can easily detect it. If there is a bidirectional error, you can easily, you can easily get marks. You can easily try this out. Like for example, in this case, there is 1 0 0 1 0 0 1. There are 4 number of ones. So the count 4 is there. If there is a unidirectional error, maybe this one is going to become 0 and this one is going to become 0. So the number of zeros in this case will be increasing. So here the number will be 4. Error can be easily detected. But if there is a bidirectional error, this one becomes from 1 to 0 and this one becomes from 0 to 1, there can be error balancing. So fault will not be detected, because still the number of zeros will be 4. So basically, so what is the idea? There is no efficient error detecting code to detect bidirectional error. Thus all designers are interested how to eliminate bidirectional error. This is the nightmare. So we have to eliminate it. So there are a lot of techniques which people have tried to do, modified codes, modified testers, and so many other things. But again, as I told you, the modified coding based techniques to detect bidirectional errors did not get much popularity because they increased the size of the circuit. And they put lot of constraints like this type of inputs can be possible, this type of inputs cannot be given, and so forth. So they have not got much popularity, and also we are not discussing in details. But very interestingly, some people have tried to do something by a very interesting way of avoiding bidirectional errors. By what? They first tried to find out why bidirectional errors are happening. Because in circuits, in communication, as I told you, bidirectional errors are rare. Because in the air, the packets are traveling due to lightning, etc. All zeros becomes 1 or all 1 becomes zeros. Bidirectional errors do not happen in communication. But in circuit it is very easily possible, as I will show you. And then people try to find out how we can avoid it. And then there is another direction of research. We try to design circuits which will not have any kind of bidirectional errors. Right? So first people try to find out why these bidirectional errors occur. We are taking a very simple circuit like an AND gate, NOT gate, etc. So these are the inputs and these are the output. Very easily you can find out basically. 1, 1, the answer is a 1. So for inverter 0, 0 or 0 is a 0. Now let us take a simple stacked fault over here. Now in the simple stacked fault over here, what happens? Basically you can see it actually affects this gate as well as affects this. Whenever a fault is affecting multiple number of output lines, there is a big possibility of bidirectional errors. So one thing you can do, you can make all circuits very much independent. That is, one individual circuit will give output, another circuit will be giving another output. That is, no such case will be there. That is basically, if something like this, if I can replicate, like for example, this is one output, right? So I mean, we can say that basically this part of the circuit is giving the output for this O1. Now for this one circuit is there, I basically this is one circuit I eliminate and I all eliminate the other part. So one circuit is just like this, right? It delivers the output of O1. Next what I can do, what I am trying to tell you is that I am not going to allow sharing of output gates. That is, for example, this output is dependent on this gate. This output O2 is basically dependent on this gate as well as it is depending on this. So there is some part which is common to both the outputs. So if there is some part of the circuit which is common to both the output, then any fault here will affect both the outputs. If we can avoid it, then it is very simple. Then a fault can affect only one output, and then there cannot be any chances of any bidirectional error. Even parity code can detect the errors in the circuit, because any single stacked fault can affect only one output, right? So what I will do that is I will try to replicate the circuit so much that there is no common, like for given one output, there is no common circuitry which is shared by two outputs. Like for example, I take this one, I have one circuit like this part is not there, this is for O1. For O2 what I have to do? For O2 what I have to do is that basically again I replicate everything. This one I am not keeping it, I will be replicating this one, this is done. So another part of the circuit, so there will be another, some circuit will be like this. This is for O1, correct, and this is X and Y, and another circuit is this one. So this X, Y and Z, this is for O2. So either so basically you can see, so this is for O2 and this circuit is for O1. So if a stacked fault, and we are all assuming single stacked fault. So if a stacked fault occurs here, only the O2 output will be affected, O1 output will not be affected. So if I keep on replicating the circuits like this, or we are not allowing any kind of logic sharing between the outputs, then you will not have any kind of multi-bit error. Forget about unidirectional or bidirectional. Any single stacked fault, only one output line will be affected, because the circuit is designed in this manner. Some group of people tried to do this, but in fact people found out that if you try to do this, there will be lot of replication of circuits, because this one for O1 this is what is required. For O2 also this part basically of the circuit is common to both. So why I want to repeat it twice? So if you are not generally will not repeat. If you start repeating the shared logics, then the circuit size will be extraordinarily high. But people have found out that if you can still have liberty, because people are trying to find out different solutions for online testing. So if somebody says that you have liberty, so that you for any given output you have no common sharing of gates between two outputs, then you can simply use parity codes and you will be having online fault tolerance. But then the circuit size become extremely high, and no designer accepted it, because I have made a very small circuit, very optimized circuit in area, and basically for testing you are extremely blowing it up. So basically the term is called intrusive design. I am again putting quote unquote intrusive. That is, I give you a design like this, then you tell me, hey, there is lot of resource sharing, and this will lead to multi-bit errors. So what I will do is that I will take this part separately as O1. So I will put it something like this, and basically this is the output O1, and for O2 basically you just have to basically have to remove this, and this is another part of the circuit which will be for O2, but there is replication of these gates. So the designer will not like it at all, because he is saying that unnecessarily the test engineer is making my design very cumbersome. So but there is one way of doing it, that is no logic sharing between the outputs. So that is one way. Another way is that people tried to find out, that is one way, people found out why bidirectional errors are there, and then they tried to avoid it by one means that just do not have any logic sharing between the outputs. And therefore, but people have dragged lot of papers on this direction, that you make parity groups and so forth. You can read on this. That is a future research, lot of work is still being going on, that instead of fully entirely separating the outputs, having no logic commonalities between these, can we make groups, then we can solve it by graph coloring problem, and n number of papers are on there. But the idea is that minimum logic sharing between the outputs. So if there is no logic sharing, no output can lead to multiple bit errors, and it will be very easy, but that will make the circuit very high. As a trade off, people try to basically see that if some groups can be made, etc. Those literature you can read on. But then another direction, people found out that, say, this is a stuck at 0 fault over here. So stuck at 0 fault means normally it should be 1, with fault it has become a 0, and in this case, so it is from 1 to 0. This is the flip direction, and in this case if you see 1 stuck at 0, so in the answer is 1, normally it should have been 0, it is 1, and here the output is, normally it should have been 0, but the failure is a 1. So it is from 0 to 1. So it leads to a bidirectional error. Then people very easily realized that the bidirectional error is happening because there is a inversion, because in this case error direction here basically, so if you look at it, so in this case the direction is changing from 1 to 0. So in this case basically if you see, this is stuck at 0 fault, okay, and in this case the direction is from 1 to 0, and is like from 0 to 1. All of this is happening because of an inversion. So people have found out that main reason for bidirectional errors are inversions. So if there are no inversions, generally the flip direction is a unidirectional process, that people have discovered for most of the topologies. So what people will try to do is that they started designing something called inverter free logic. So if you just remember this circuit, so this is what the circuit is. Now, and people, you will be also able to appreciate that this actually is creating the problem. This inverter is mainly creating the problem, and that is why there is a bit flip. Now what people have tried to do is that they will not put any inverters in this circuit. That is called an inverter free design, because from one direction 0 to 1, other line 1 to 0, obviously because of inversions in this circuit. Some people tried to use De Morgan's law and put all the inverters out of the circuit. Like this is very fine, this is logic, this does not, O1 does not have any inversion logic, so you can directly put it. But in this case, basically if you look at it, this part of the circuit is an inverter logic. In fact, it is nothing but you can tell that here is a NAND logic. So this is a NAND logic basically. So this part is a NAND logic. So this is the input, this is the OR gate 2, this is the OR gate number 2, and in fact the input, this inversion and an inversion, which is the second input, the first input to this OR gate is a NAND logic. This is a NAND logic. So NAND logic can be very easily implemented by De Morgan's law. You invert the inputs and use a OR gate. So in fact, obviously you cannot design a circuit without inverters, not at all possible. Of course, because for NAND, inversion is required for a universal gate design. But what they will do, they try to bring out all the inverter logic out of the circuit, and here you will get X and here you will get X bar. So I have put some inverters here, but in reality the circuit output, or basically you assume that there is a machine which will generate X and X complement. Then you are assuming that is error free. Of course, I always keep on saying in all my lectures that you cannot create magic. So in this case, a circuit can only be designed with inverters, because inverters are universal logic, are involved in universal logic. You cannot design any circuit without inverters. So what here they have tried to do, they are not putting any kind of inverters inside a circuit. All the inverters are pushed out by using De Morgan's law, but still inverters will be required for giving inputs. So basically there is some circuit, like this is X and this is X bar. There is some circuit which will generate X and X complement and give to the inputs. I will not put any inverters. Just for showing it, I have put some inverters over here, but you have to know that there is some device which will create X and Y, and also X bar and Y bar. So there can be feed over here, that is X bar and this is Y bar. So if you can do as a homework, as there is no inversion over here, there will be no flip flops. Sorry, there will be no inverters, so no stuck at fault will lead to bidirectional errors, because bidirectional happen means one is going from 1 to 0 and is going from 0 to 1. So there should be inverter logic. So all inverters, if you push out of the circuit, then there will be no kind of bidirectional errors. So if I keep on telling this story, there are hundreds and thousands of papers which has come out how to handle bidirectional errors. One, as I told you, circuit replication, that is, do not share any logic between the outputs. Another way is that you push out all the inverters to the output side, and basically you apply signals x bar, y bar, whatever, both versions you have to give as input to the circuit. N number of different techniques has been found out which basically eliminate bidirectional errors, because detecting bidirectional errors are very difficult and you require very complicated coding theory to that. So a group of researchers, or most of the researchers in online testing of embedded system case, tried to avoid bidirectional errors. Like one I am telling you, by avoiding sharing of logic between the outputs, pushing all the inverters. There are some of the major techniques. Lot of other techniques are there which you can read. References will be given in the course, so you can do it. But this, I think, by these two examples, you have got an idea that what is the coding theory, how it is applied in circuits to test online by error detecting codes, and what is the problem of bidirectional errors and how they can be avoided. Some basic techniques, or the first line or the premier techniques which were discovered at the baseline of those online tests by error detecting codes, I have told you basically. So more or less this is in your syllabus, that if you want to know more, there are n number of research papers on handling bidirectional errors, different type of coding theory, etc. If you look at it, for bidirectional circuit or handling bidirectional errors, people avoid it. To avoid it, some way you have to change the original circuit. Like one is basically, as I told you, you have to separate the outputs, so that no output, there is no logic sharing between outputs. Here you have put the inverters toward the outside, and by that you have to apply a lot of De Morgan's law in the gate. In all these mechanisms, basically the original circuit will get changed, and in modern days no designer will allow so much changes to your circuit for getting it online tested. Of course, some changes are allowed, but massive changes like putting all the buffers outside, no logic sharing, nobody is going to take it. Actually, they are called intrusive designs. So there is a lot of tussle between the test engineers and the designer. How much intrusivity will allow? I am a designer. I have given a circuit which is optimized in area, timing, and power. The test engineer is changing a lot of designs in my circuit. I may not be like to do that, and in fact, the changes allowed are very minimal by the test engineer. So therefore, in modern community of online testing, this error detecting codes are not that much accepted. This was some around 10 to 15 years back. This was a good techniques to be applied, but nowadays people are not very happy with it because it involves lot of changes in the circuit which we are called intrusive designs. So now with this we stop the basically discussion on error detecting codes. We will see how another group of researchers, how they are handling online testing, and their main emphasis is to keep the circuit intact. That I am not going to change your original circuit, maybe slight changes I will do, but very minimal. But of course there cannot be any magic. So these people are involving more number of area overheads compared to the bidirectional error detecting code theory. The best advantage of error detecting codes for online testing is the low area overhead. That is very important, and test coverage is very high. So if you assume that I will not have any bidirectional errors, or I design a circuit so that bidirectional errors are avoided, in that case the fault coverage is very high. But as I told you, intrusivity is not liked by most of the design engineers. So some people thought of handling it in a very different manner. So they started from very fundamental design, that how I can do online testing without changing the circuit itself. Very interesting is replication. Normal circuit is there, you replicate the module and make a comparator. So if both of them are giving the same output, there is no error. If there is somebody is giving a different output than the other, there is some problem where the error is. Of course you can detect it. To make a more robust, you can put module 3, same thing, same input will be going over here, and comparator is, instead of a comparator you take the best of 2 votes. So all no problem, all 3 are giving the same answer, no problem. If there is a problem, you take the majority vote. The assumption is most likely only one of them will develop the error. But in this case the area overhead is becoming very high. Then people started thinking about partial duplication, that why unnecessarily want to replicate everything, because anyway in case of error detecting codes also you are making very strong assumptions that only unidirectional errors will be there. That means I am restricting the stacked faults which will lead to only unidirectional errors. So that means still again in the coding theory also I am compromising on the fault coverage and detection latency. I will cover more on detection latency later, but still there is a compromise. So why not I make this module, instead of 100% replica, I make 10% replication. Then only for the very important parts of the circuit which are required to be tested, I will make a very small replica. Error detecting code also compromising, I am also compromising. So therefore they call it basically a partial replication. So in this case what people do, they take a circuit like this, go for ATPG, find out all the test patterns, then they use a subset of these vectors to design the proper replication circuit. Like for example, there are 100 test 1000 test vector 100 test vectors say for module 1 to test all the faults, and say that somebody says that only 10% area over I will allow for testing. You take the most important 10%, that is 10 test vectors which are most important, that they have the maximum coverage. Like in BEAST already I have told you how to select good test vectors. So use only those test vectors, because in online what happens, all the inputs are going to come. So at present say that maybe actually 1000 inputs are possible, and among them I have found out that these hundreds are enough to test all vectors. Or in, let me tell in other direction, say 1000 different type of inputs can appear over the circuit. So if I want to go for a 100% guaranteed zero detection latency, everything I want to do it, you have to just replicate the module, then everything will be very good. But for example, somebody has told me that I have only a restriction of the only 10% area over it, and then if you go for an ATPG, then you find out that 100 test vectors are enough to test this circuit. But among these 100 test vectors, maybe only 10 I can keep, because the area over it has to be very, very small. So I will take say only 10% of 100, that is 10 vectors, and I will design module 2. So module 2 will be a replica of this circuit, but it will be a miniature version, because only if these 10 important test vectors are appearing in the circuit, I will do the test. Because you cannot apply any test vectors, online testing, vectors are coming. So whenever these important test vectors come, then you have to go for the comparison. That is the idea of basically partial replication, that take only the important test vectors, and basically whenever those vectors are coming in the input, because you cannot control the inputs, then you go for testing. But the efficiency strongly depends on the prior knowledge regarding the input test patterns that the circuit is likely to receive, as well as that occur rarely. Because these 10 may be very, very important test vectors. You design a circuit with these 10 test vectors, but these 10 test vectors never come in the circuit. Because if I were the test engineer and I have an ATE or a BEST, I will apply these 10 test patterns. But in online testing, the inputs come, and among them, if something is good vector, you have to test it, or I should not call it good, if they are in this module, then only the testing is possible. Because in this module, you are keeping a very small subset of the test vectors on which the test comparison can be done. So these 10 vectors are very good, no doubt, they are very high fault coverage, very good points they test and all these things, but in the normal scenario, these 10 test vectors never come. So in this case, you have very good tester like module 2, but inputs may not arrive that manner, which will be testing your circuit. But if it was an offline test or a BEST, then I will apply this test one among these test patterns, I will apply, but online testing you cannot apply. So therefore, efficiency will strongly depend on the prior knowledge, that whether these important test vectors will come. So the problem is twofold. First, you have to find out very good test patterns which are very efficient, and secondly, you have to find out whether they will occur at regular intervals or not. If it is possible, then only you can make for efficient partial replication based test. But what is the advantage? Its advantage is non-intrusiveness. That is very, very important, that I am not going to do any changes in the original circuit. Circuit is there, a part of the circuit is there, you are making a comparison, only for the partial part which you have replicated, the testing can be done. The advantage is non-intrusiveness. So again I am telling you, nowadays online testing is mainly done by this partial replication based method, because no test engineer or design engineer will allow you to do massive changes in the circuit, nobody will allow you to do that. So therefore partial replication is now becoming a de facto standard of online testing. Without going into more theory, let me give you an example. This is a circuit, you can go over to that, and basically there is a fault over, the stacked fault over here, right. So this output is basically V1, prime is V1, V2, V2, V3, and this is the output for the second. So in this case again, I mean you can just, we always try, you can see this is one part of the circuit and this is another part of the circuit. There is something called cone of influence. Cone of influence means what is the subpart of this circuit which actually influences the output. Similarly, if you look at it, this is the one output of a circuit, and these are the gates which actually impact this output or control the output. So this is actually gates are in the cone of influence of this output, and for this output V2, this is what is the cone of influence. So cone of influence is very simple, you take an output of the circuit and what are the gates and nets which actually control the output. That subpart of the circuit is called cone of influence for that output. So this definition we will be using, so I am just telling you it in brief. Now I will make a finite state machine. Later I will tell you how to handle this finite state machine in complexity. So they have, if you look at it, this is the normal finite state machine, and this part corresponds to the fault finite state machine, because now a fault has occurred. So without the fault, basically the machine will behave like this. So there are 1, 2, 3, 4 states, basically 2 flip flops. So there are 4 states, some state may be unreachable. We are assuming that the state starts from 1, 0, and basically with the input 0 it will come over here, because this input is only one, that is V3, and V1 and V2 are secondary primary input, that they are feedback from the flops. So basically, if the V1 and V2 are the state register values, so the present state is 1 0, that is if the present state is 1 0, and basically if the input is 0 or 1, you are going to get the next state as 0 0. So even if the present state is 1 0, the input is 1 or 0 anything, the next state is going to be 0 0. That is what is showing by this line. Anyway, this is very self-explanatory, simple digital design fundamentals. But with a fault, now I am going to draw the finite state machine with the fault. You will appreciate that you have to clearly do it. By analyzing, you can easily find out that basically there is only one transition which is different from the normal compared to the failure. What is that one? If this test, if the present state is 1 0, that is present state is 1 0, and the input is basically a 1, the input is basically a 1, then in the normal case the next state is 0 0, but the fault case it is a 0 1. So normal state the out so 1 0, so the normal case it will be going to 0 0, but for the fault case it is going to the next state, that is 0 1. This is again fault case will be 0, but this case is going to be a 1. So this one, as you can easily see, this fault is only affecting this cone output, so there is no effect over here. So in this case the from the present state is basically, if you look at it, 1 0, so present state is 1 0, the next state is always going to be a 0 if the input is a 1 irrespective of the fault, but in this case basically if there is a fault, the output is going to become a 1, and in the normal case the output is going to be a 0. So normal case 1 0, the input is 1, is 0 0. Faulty case, same state, same input, the output is going to be a 0 1. So basically we call this as a fault detecting vector or a test vector, because that is can differentiate between the normal and the faulty behavior. It is nothing but your simple normal ATPG you can do and find out the vector which differentiates. This is just the procedure I am going to show you, that how they go for an online tester design. By this method, partial replication method, they are taking this procedure. You can also find this vector. The vector is basically nothing but initial state, that is 1 0. So 1 0 is the initial state. Present state is basically input is 1. This input is a 1, and basically the next state is basically a 0 1 in this case of error. That is 0 1 in case of error. Normal case it is 0 0. This is error. This is normal. So this one you can easily find out by your normal ATPG mechanism also. But in this paper, the theorem or this theory I am discussing is basically on the online testing design in finite state machine. So they handle it in a different way, and then they will remove the complexity. But you can take it from me, but the same test vector can also be found out by ATPG or by n number of different techniques are available. Like normally we have done by scan chain, method you can do it. Also by basically you can that is what we call time frame expansion method. Any method you can use to do it. But for the time being, we can find out that present state is 1 0, input is 1, next state 0 is the fault detecting line. So that is what actually is going to detect the error. Now they are going to design an online tester to detect it. So that for the time being, let us assume that there is only this, because in this case there is only one edge which is actually detecting the error. So very easily you have to detect, this is the only one which detects the error. So you have to design an online tester using this mechanism or by using this FD transition. So the job is make a normal version of the finite state machine, make a faulty version of the finite state machine, collect all such FD transitions. FD transition means fault detecting transitions. Collect all such transitions which are making a difference. Using those transitions, you will make a module 2. That is what is our module 2. This one you are going to make, module 2, which is going to detect the errors online. So how do I do that? This is the finite state machine design of the test vector for this. The algorithm is simple. Take a normal model, finite state machine model, all fault finite state machine model, collect such FD transitions. In this case, there is only one FD transition, and using those FD transition, you have to design module 2. This slide actually shows the design of that tester. So what you do? Keep this initial state. This is the online tester. Module 2 design I am teaching you. So basically, this is the finite state machine level implementation of the tester. So what it is doing basically? So what it looks is D0. D0 is this is the machine model of the circuit under test, and module 2 design basically is this FN detector, right? So now this is a tester. So what the tester is going to do, at the initial state of the tester, you are always going to track whether I am in the state called 1 0, state encoding 1 0, because only from this state basically such a vector is there where a fault detection can be done. Otherwise you need not do anything else, the detector can sleep. For this, for low power. So what they do, this design, if you look at it, this test And basically if you look at it, this tester will basically probe the values of all the state variables and the inputs. Of course, so the tester has to probe the values from the circuit under test so that it can detect it. The obviously, and as the tester and the circuit both are on chip, you can do that. So if I say that this is the tester, that is module 2, so it is going to probe this value, is going to probe this input, as well as it is going to probe this input. So with this it can do testing. So what it is going to study? It is going to study if the input bit is 1 0, from where the fault can occur. So it is saying the initial state is keeping the track of the next state. So it is always keeping a track whether in the next state it is going to be the value called 0 1. 1 0 is the state from where the error can be detected. So always 1 0 here means the next value it will be 1 and 0. So these lines I am tapping, these two lines I am tapping. So the module 2 of the detector always try to find out if there is a 1 0 in V1 and V2 respectively. Is such the next state is going to be 1 0 from where the fault detecting transition is there. So it is always trying to see this case, that if it is 1 0, the third bit is basically for the input line V3, which is immaterial in this case. So always I am going to check whether it is a 1 0. It is a 1 0, very good. I am going to the next state of the tester. This is the next state of the tester, not the machine or the circuit. So I am going to get D1. D1 is a very interesting state, because in D1 the initial state is always keeping a track if the next state is 1 0. If it is a 1 0, then only the tester will wake up, because the fault detecting transition is only occurring from the state 1 0. Otherwise else it is going to sleep. 1 0 has come. Very good. That means the machine in the next state is going to be either in this state or this state. That is the same state called 1 0. Then it goes to the intermediate state. And in the intermediate state, what is going to try to study? In the intermediate case, it has to study that if the input is 1 and the next state is basically 1 1. That is what is the error. If you look at, this is the error. Let me clean it for you. Next state I have to, this is the error, that initial state 1 0, input is 1, the next state is 0 1. So first it has tracked that the circuit is now going to be in the state 1 0. Next, what is to find out the tester, that the input is 1 and the next state is 0 1 instead of 0 0. Normal case it should be 0 0, but for the fault case it has come to a 0. This is what is actually going to be tracked. So you see, first it is tracking 1 0. Next it has to track that it has gone, let me zoom it for you. The 3 bits of the tester, first I have to tell you, the 3 bits of the tester is something like this. It is the first 2 bits of the tester are the test state registers, V1, V2 probing, and the third bit is the input, that is V3. So it is in this case 1 1 1 1 3. This is the vector called 1 0, input is 1 and the next state is 0 1. So if this is the case, the error is being detected by that fault detecting transition. So what I am doing is, initially it is probing all the 3 lines, V1, V2 and V3. So V1, V3 is 1 0, that means the circuit is next time going to be in the state called error detecting state, that is 1 0. So in this case you will go to an intermediate state of module 2, that is the tester. It is very happy that it can happen that from this next state the fault can be detected, otherwise it cannot do anything, it will be looping it up. Okay, fine. The next state is going to be 1 0, it is coming to an intermediate value. Now what is going to track? It is going to track that the input, that is V3, basically is going to be, as I have shown in the arrow, it is seeing V1, V2 and V3. So it is going to see that the input is 1, very good, this is the input, and the next state is going to be 0 1. Then it is actually a fault, because in the normal case it should be 0 0 1. Input 1, the output state registers are 0 0. In such case it will again go back to the initial state of the module 2 of the tester, it will again go to sleep. But if the fault is there, then from state 1 0, the next state is going to be a 1 0 1 and the input will be 1. That is, this part is matching. This one actually corresponds to this, and this input V3 and the output 0 1 is corresponding to 0 1 and 1, and the fault is detected, and you will land to the final state where the output is a 1. This is the output of the basically of your tester, which says that it is a fault, right. See, all other cases the output is basically a 0. This is also a 0, this is also a 0, this is also a 0, but here, from here it is going to the last state of the tester, it gets stuck over here because the fault has been detected. Basically if you look at it, so in the initial state, that is D naught, you can see keeps a track of the next G state. So that is, it is going to find out whether a state has come in the circuit from where the error detection is possible. In this case it is 1 0. But intermediate state, go to an intermediate state when the cut is in a state from where there is an FD transition. So it is tracking that 1 0 is possible or not in the next case. That means now the circuit has come to a state from where error detection is possible. So the tester is going to go to the intermediate state, and final state basically if an error is detected, that is 0 1 is the next state and 1 was the input. So in this case the fault is detected, and then you will get stuck in the tester saying that the error has been detected. The output is actually telling you that error has occurred. Okay, and if it happens that basically this, if the circuit is normal, you are going to get value of 0 0 1. This is the input and this is going to be the next state. So it will again go back to D naught, that is corresponding to L0, and the fault is not flagged. That is what is the design of an FN detector, and this actually corresponds to only this single transition. We have to repeat this for all the transitions. How many? In this case there is only one transition which is detecting the error, which we are calling FD transition. In a general case, as next example I will show you, there can be n number of such transitions. For all of them you have to build a tester like this, and this tester is a finite state machine. You will be synthesize the circuit and it will correspond to your module number 2. So that is the tester module. Now you can ask me a question, basically that a finite state, because we require a finite state machine model to do this, and finite state machine model for the circuit we are making a finite state machine model for this, but actually it is to test explosion. How can you handle it? So this group of people working on this partial replication based online testing has given a formulation that the same thing can be done symbolically, and I am not going to go in very details of this because already this has been taught by Professor Deka in symbolic model checking. In symbolic model checking, what we do, we do not go for explicitly finite state machine model of the circuit, rather we represent it by a, what do I call as a binary decision diagram. So what they will do in this case, I need to just find out these fault detecting transitions. So what they will do, what is the step? Partition the circuits into cones of influence, generate OBDD correspond to the cone circuitry under normal condition. That is what, this is the circuit. So you take a cone like this, you take a cone like this, you generate, you represent this part as a BDD, normal mode, and also all the cones you represent by BDDs. That is a symbolic representation of the finite state machine. Then you make a faulty representation of all the BDDs, and then you XOR it. And then basically if you XOR the normal and the faulty BDD, all paths leading to the one of this BDD is going to be the test vectors which differentiate the fault. Example I will take. So partition the circuit into cone, generate OBDD correspond to the cone under normal condition, generate OBDD of the cone under faulty condition, XOR the two OBDDs. The value of variables corresponding to the paths to leaf node 1 are the input combinations for every transition. That means those input combinations basically differentiate the normal and the faulty condition. Very similar to symbolic model checking which Professor Deka has taught in details. So I will just going to give you an example over here. In this circuit, if you look at, basically if I remove this, so this circuit if you look at, so this fault has no impact on this cone. So in fact I may not use it for this example. Basically I am interested in only cone number 2. So in cone number 2 basically, so I will represent V2 in a BDD in the normal mode. So this is what is the BDD under normal mode. So I am calling it V02, basically just to represent a normal mode. If for failure I will represent by 1 2. So 1 corresponds to the fault, 0 corresponds to the normal number 1 for the first fault, second fault, third fault. I can just represent a simple nomenclature. So if you look at this, the BDD representation of this cone, simple Boolean algebra, right. Next what I will do, next I take this Tacket fault over here, I take this Tacket fault over, the Boolean representation gets changed and I generate another BDD. Just this is a homework, you can take this circuit, find out the Boolean binary representation and represent it in BDD. Already in details we have taught you in the verification part of the course. So this is the cone representation for the fault and this is for the normal. Now you do an XOR. So this will be the XOR representation. So now it is very important. So XOR means this is the BDD representation of the normal normal BDD, faulty BDD. I am XORing. So any path it leads to 1 means this is the vector which leads to different values in the normal model versus faulty model. BDD version. Of course, BDD version is the representation of the circuit version. So very simple idea. Normal BDD, faulty BDD, XOR, any path leading to 1 means basically the XOR value is 1. So when the XOR value of 2 Boolean representations are 1, if there is a difference in the output. So therefore, look at V1 equal to 1, V2 equal to 0 and V3 equal to 1 is basically the vector which represents a difference in the normal and the failure mode. So that you can find out by this. Now how we are using representing a FD transition like this. So already we know what was our FD transition. Our FD transition is nothing but 1 0 1 and 0 1. This is our FD transition. So if you look at it, if you look at your vector, what we have found out V3 equal to 1 and V1 and V2 is 1 0. So 1 0 1. So it is, see, so this is V3 and this is basically the values from here. So in this case V1 is equal to 1 and V2 equal to 0 and V3 equal to 1. So that creates a difference. Sorry, let me go to the FD transition. So here also you can find out, or also FD transition if you look at, we can get the value. So this one is V1 equal to 1, V2 equal to 0 and V3 equal to 1. So that is the FD transition. That is, from this present state, if the input 1 is applied, the error can be detected. The same thing I can also find out by this one, V1 equal to 1, V2 equal to 0 and V3 equal to 1. This corresponds to the present state and this corresponds to the input. So instead of using a finite state machine representation, basically here I am using this I have found out by basically a FSM representation, that 101 is creating the difference. But the same thing I am also finding out by basically a symbolic representation. This tells you that this is the present state and this is the input from where the basically error can be detected. But what is the error effect? How do I find out what is the error effect? So error effect basically this tells you that this vector V1 1 0 1 state and this input is going to lead to an error detection. That is basically nothing but this point, that this is the state and this is the input where the error difference is there. But what is the final output, that how the error is reflected, that is 0 1. How do I find out? That cannot be told by this basically in this BDD. This BDD is just telling you that this is the input condition in which the error can be detected or the difference is there, that is this one. Now how do I find out the error representation? Error representation is 0 1, that is V1 and V2 is basically this one. How do I find it? It is very simple basically. You take this vector and apply it here, because this is representing the cone. The vector is 1 0 1. This is the present state, this is V1, V2 and this is V3. So this is nothing but the BDD representation of the cone under fault. So if this is the input, what is going to be the output reflection? Very simple, you put here as a 1, V2 is equal to a 1 and V3 is not required over here, thus the answer is a 1. So what it is saying, that 101 basically can detect the error, that is found. But what is the error output? For that you have to just take this bit and apply in the circuit or in the BDD. You can apply in the circuit also, will tell you the value. So I am applying the value 101. Under fault you can easily find out from the vector itself, BDD itself. So this is going to give the value of a 1. So this is going to be the value of a 1. So this is 1. So the value is 0. So I have made a mistake. So the value is a 0. So what is the value? V1 equal to 1, V2 equal to 0. So I have to go by this path, and V3 basically is 1. So V3 is basically 1. So this is the path I have to basically take. So this is going to tell me, so V1 equal to 1, V2 equal to 0 and V3 is equal to 1. So basically it tells that the output is a 1. So the next state output is going to be a 1. Similarly, if I want to find out what is under error, what is going to be the value of? So again I am just telling you that basically this one actually tells you, this part actually tells you that this is the input condition in which case the error can be detected. That is V1 equal to 1, V2 equal to 0 and V3 is equal to 1. But what is the impact or how the output is represented is not told by this BDD. That is, if I apply 101, that is the present state and the input, the error can be detected or differentiated. But what is the output? I have to find out. For that you have to take this vectors and apply in the circuit. Very simple. Output is 101. So I will take this input here and apply. See, it is saying that is 1 and it is 1 is the input and the number is basically 1 0. So this is 1 and this is 0. So this is 1 and this is 0. So this is the BDD has told me that this input and this state condition can detect the error. But what is the error output? You have to just apply in the circuit and you can find out. If you apply it, you will be very easily able to find out that it is nothing but the answer will be a 0 and a 1. This is basically the error output. This again repeating, the BDD has told you that 1, 0 and 1. This is the error detecting code or FD transition input condition. But what is the effect? That the BDD will not tell you. You have to just apply this value to the circuit and you can find out what the error output. So in this case it is a 0 over here. If you apply this, you can easily test it and the answer is a 1 over here. Had it been normal, you are going to get the value of a 0 over here. So very simply, you do not have to go to the finite state machine at all. So what I am going to do? I am going to take basically the normal condition, because this is the cone only I am interested over here. But in general case you have to repeat it for all the cones because the fault is over here. So I am just interested in this cone. So I am going to generate the normal cone, BDD representation of the normal cone, faulty cone and XOR it. So if you are XORing it, you are going to find out the input condition in which case the fault can be detected. In this case it is 1 0 and 1. Now I will take this vector and I will basically apply it in the circuit with a simple simulation. So what is the value? 1 0 where the error can be detected and the input is a 1. I just simulate the circuit and it will tell you, simulate the circuit of course with a fault, it will tell you that the answer is a 0 and a 1. And if the error was not there, the answer would have been a 0. In fact, I am not interested in this part. So this will actually give you the FD transition. So 1, 0, 1. This is the FD transition, initial part, error detecting part, that will be told you by the BDD, but what is the output in case of an error will be, that is actually 0, 1 will be found out by simulating the circuit. Circuit simulation is very, very simple complexity. You need not at all bring the FSM into picture, but very easily you can find out the equivalence. You can see 0, 1, 1, sorry 1, 0, that is 1, 0, apply a 1, the fault case is 0, 1. So this is the same thing I can find out without applying the BDD. Sorry, without applying the finite state machine. So this partial replication, what it does, again just I am repeating. So you take a circuit, you take the normal model, finite state machine model, find out the vector or the all transitions which are related to a difference in case of normal and faulty representation. Using this, generate the FN detector, that is which tries to detect or which tracks the FD transition, that is initial state, it will try to find out whether the circuit is in this state. Next state is going to find out whether the input is this, and the next state is going to be this, so the error can be detected. That is what is the job of the FD transition. And FN detector which uses an FD transition. Done. Synthesize it, your tester is ready. But the problem is how to generate these test vectors or these FD transitions. Very difficult because we are doing as FSM. People have avoided it by using a BDD based approach. In this case, what you do? You divide the circuit into cones, take the normal BDD, faulty BDD, XOR the BDD, and it will tell you what are the input states and input combination which can lead to the error detection. But in this case is 1, 0 and 1. But it will not tell you that what is basically the outputs of the circuit corresponding to that input FD transition condition. For that, simply you have to apply these state values, like in this case 1, 0, and the primary input, it will get the error value, that 0 and a 1. And use this, you can avoid state space complexity, and still you can design basically your FN detector circuit which will be an online tester to the system. In this example, I have shown you a case of a fault in which case there is only one FD transition and you design it. But it will not always be the case. As a simple example I will tell you. But what are the advantages? The design of the FN detector does not change the original structure of the circuit. So it is a non-intrusive design. That is the key challenge, that it does not change the circuit at all. You just take this, and basically the FN detector will be something like this. If you synthesize this FN detector, it will just probe this line, it will just probe this line, and it will just probe this line, and it will concurrently run with the circuit. So it need not change anything. If you look at the structure, it just probes the 3 lines, that is V1, V2 and V3. Just observes these 2 state lines and the input lines and tries to track where the circuit is going. So there is no change in the circuit itself. So it's a very nice design. But you can see one thing you have to appreciate, that this FSM is also not very small. For each such FD transition, we will require a small FSM structure like this. Of course, I will do a lot of FSM optimization can be done, but still the FSM for the FN detector or the tester is not very small. Its size will be much larger compared to the error detecting codes or finite or signature monitoring, etc. So this is a partial replication based method. So always you have to appreciate the fact that partial replication based methods are always higher in size compared to the other counterparts. So basically, if you look at, so what I have done, I have taken a circuit either represented by FSM model or by BDD. I find out the FN detector and I represent a fault detecting detector which is going to be synthesized as a circuit to do the online testing. But this circuit is not very small compared to the original finite state machine. So the FN detector or the tester will be very comparable with the CART. How do I avoid it? But the key role I have to appreciate here is that it is a very online, very non-intrusive design. That is a non-intrusive design. It just draws some lines from the circuit under test and takes the decision. FN circuit is going on, the FN detector is basically tapping some lines from the CART, that is the state lines and the input lines, and trying to find out whether the circuit behavior is proper or not. So that is the key role of partial replication. So any circuit with a partial replication based architecture are non-intrusive, but the circuit size is much higher. So what I can do? So because anyway there is a not magic. So either you have to take a very large circuit to go for non-intrusivity and good fault coverage, the tester circuits will become larger. But if you want to bring the tester circuit down and go for the coding theory based approach, then lot of assumptions come, like either the circuit has to be modified so that there is no bidirectional errors, and so many constraints come in, making the circuit design intrusive. So that people do not like. So this partial replication based circuit is very good. Circuit does not require to be changed, which is one of the foremost important requirement. I design a circuit for testing. If you want to change it, I may not be very happy with it. So therefore, partial replication based testing and gain a lot of emphasis in the real world. So in this case, but how do I trade off? Because you have a circuit but a very big FN detector, not good. So you drop some FD transitions. So in this example, I had only one fault and one FD transition. But in a real case, for given faults, a lot of FD transitions will be there. If you want to, and the circuit tester size will become very high. What you can do? You drop it. Some you blindly drop so that the area of the circuit comes. But which one you will drop? Another research area. That which are the important FD transitions. FD transitions are very much correlated with faults. This fault, so many FD transitions. Then you try to find out which are the most important faults. You keep only them. Other non-important faults you do not at all bring into the picture. Also for the given faults, there are say 10 FD transitions. Try to find out which FD transitions occur frequently. Because as I told you, say for example in this case, there is a state in which case this is unreachable state. Right? If the initial is unreachable state. So we should not take any kind of FD transition from that state, because under normal conditions the circuit will not reach that state. So even if there are some FD transitions starting from the unreachable states, you may drop. So look at the quality of the FD transitions. Good quality FD transitions are the ones which occur very frequently. So because in online testing you cannot control the inputs. So whatever inputs are coming, based on that you have to take decisions. So every transition occurring frequently, you keep it in the tester. That means then you will be a very high probability of getting such transitions coming in the circuit under test, and you can detect the faults. Occurring rarely, FD transitions you can throw out, like the example I have given you, unreachable state. Throw out all the FD transitions starting from those states, because anyway the cut will never come there. So lot of trade-offs are possible by controlling the number of FD transitions. On the contrary, in case of error detecting codes, you do not have much control. That is, you assume that you take a coding theory, it will detect odd number of unidirection error. You take another coding theory, it will do this. So based on the error detecting code, you have to basically take the flexibility. But in case of partial replication, the flexibility is very, very dependent on the test perspective. Because in the error detecting code based techniques, the trade-offs like unidirectional, multidirectional, odd detection, even detections. So some of the techniques I have discussed, all of them will depend basically on the coding technique used. That is going to give you the trade-off. But in case of partial replication, the trade-off comes directly from the testing perspective. 100 FD transitions are there. Which one I want to keep? Because more FD transition, the tester design will be larger. So you drop all the FD transitions which are from the states the circuit never reaches. Some FD transitions remain. Keep those FD transitions which occur more frequently. So you can understand the trade-offs are both from online, both in the partial replication as well as in the coding theory or whatever technique is possible. But in case of partial replication, the control is more, just by controlling just by taking the number of FD transitions or dropping some of them is the control phenomena of the area of the FD transition. But this controlling the FD transitions or by taking some of them and dropping some of them is directly related to the faults and test. So it gives you a more better control over testability compared to your coding theory. So therefore partial replication based online testing is very good or much better compared to coding theory. So the area overhead and the power of the detectors are reduced at the cost of higher detection latency. Why this? What do you mean by latency? Here I have to come to the fact that what is a latency. Say, let me just go to an example, it is better. Another example I have taken with a Stacked E fault. Look at this. This one is very, very important. Same thing, but in this case, basically there are 3 FD transitions. One from 0, 0 input is 1 this way, 1 is another, and this one is 3. You can, I am not going to the elaboration, you can easily look at this circuit and you can find out that these 3 are the FD transitions or the cases which differentiate the normal and the faulty behavior. So if you make the FD transition, so there will be 3 parts. This is for the first transition, this is for the second, and this is for the third. So for the same behavior, same pattern, so everywhere you have to track that whether this is going to be my state. If it is so, I have to wake up and you have to just find out whether in the next state the input is 1 and you are going to this state, then the error is detected. Same idea of FN detector design, but more number of FD transitions, more number of states in the FN detector machine, so higher will be the circuit of the tester. Now how do I compromise? You drop one FD transition. Let us assume that I am going to drop maybe these 2 FD transitions. So basically maybe this will be there and these 2 portions will be dropped. So your FN detector state machine will be small because you have dropped some transitions. Now what will be the impact? The impact will be because I have no control on the operation of this finite state machine. It can go over here, it can go over here. I have no control because the inputs are coming from the environment and the circuit is traversing these FSMs. So it can happen that what it can happen is that it may come here, it may go here, it is going totally traversing over this. I have no control. But sometimes among this, maybe after so many times, once it takes. And for the idea of trading of this area of the tester, you have dropped this FD transition. You have not considered this FD transition in the detector design. So what it can happen? So basically it will revolve over here, then this one is happening. Error has occurred. Instead of basically this has occurred because this is what is showing that this is a difference from the normal behavior. Error has occurred, but you will not be able to detect it because the detector does not take account of this transition. So now the error detection latency. Then again you have to wait for a long amount of time. Maybe after this you will be going over here, and here, and maybe after some time it may go over here, because in this, just assume that there is there is a basically transition from here to here, just assume, then you can go here from here, then assume that this I have kept and this I have not kept. So still it is going around here, it comes over here, fault is flagged off, that is error has occurred. But again after that what happens? Error has occurred, but now it is revolving in this manner. I am not able to detect any fault because there is no behavior difference, but the fault error has started its place because it has taken place. I am not going to detect it. After that, assuming that there is a transition over here, just assume, then after some time this transition has occurred and your FN detector has detected it because this is captured in the FN detector. Then you can flag off an error. So there is now a lot of latency because whenever this transition has taken place, the error effect has started. But again it was revolving in this manner, so error was not captured. Even in between, this one might have again occurred because nothing can be done because you have not taken into fact of this transition in the FN detector. But after some time, after a lot of time, say it has gone to this state, and from where this error transition again occurs, and basically now you can detect the error because that is there in the FN detector. So some time has passed. So that is actually fault latency. What is fault latency? That is fault effect, the effect to detection. This is called fault effect to fault detection. So this difference in time is called the latency. It's simple, very simple, so I am not defining it formally in the course, but latency means error has occurred and the effect is observed and when you detect it. So you can very easily appreciate the fact that if I take all these three FD transitions, like in this case, the direct detection latency is 0 because it has come over here, gone over here. Whenever the fault effect happens, you can easily capture it because all the FD transitions you are keeping in the FN detector. But if I remove some of them, then there are very good chances of basically your elimination of error detection latency, because for example, as I told you, if you have not taken this and you have taken only this and this, you have not taken this, only this, then you have to wait till this occurs and your fault is getting detected. In between, the FN detector, FD transitions will occur, circuit fault will be shown in the circuit output, but you will not be able to detect it because I have not kept into picture. Now if you ask me a question, obviously if you should to take all the three, but the size of the FN detector is becoming higher, cut size will become compared to the tester size. So reduce it, I have to drop some FD transition. If you ask me which FD transition I should reduce. So if you look at the fact, here in fact, if you look, if once I reach over here, after that I cannot reach back this state. So this transition occurrence probability is very, very low. But if I am in this loop, so once I will be here, I will come over here. And after that, if you see, I will be looping in x12 and x14. So I will be either looping by this manner, and sometimes this and sometimes these transitions will occur. So a probability of occurring of these two transitions, basically this and this, probability is much, much higher. By looking at the state structure, I can tell you. So if you give me the choice that you have to take only two FD transitions, I will of course take only this two. If you give me the choice of taking only one, I will basically take any one of them two, because once the fault happens, then the probability of moving in these states is much, much higher than moving in the state 1-1. So if I am going in state 1-1, basically, then only this FD transition can occur. So probability of occurring tau 1-2 is much lower than the probability of this and this. I will take this two. If you ask me to take only one, then I can take either this or this. But if you allow me to take all three, then only I am going to take this. So these are choice. So you have to look at the structure of the FSM and then find out which FD transitions are more probable to occur. You try to keep them. Best to keep all, but it will make the area very high. So you have to trade off that Which one I have to consider. So now this is actually with respect to the probability of occurrence of FD transition, and this is corresponding to this fault. Now for all faults you have to repeat this procedure. So if you ask me which faults to keep and which faults not to keep, that is very simple. Which are faults very important and somebody told you they are most frequently occurring in your online operation of the circuit, just take these faults, all others you drop. So therefore what it tells, basically this partial replication based circuits idea is very simple. You take circuits, take the important faults, find out the FD transitions, design the FN detector, drop all FD transitions whose probability is lower. So I have a very good control basically of designing a FN detector, that is a tester, with much lower area over it, that is partial replication, than the circuit itself, but I have a big control that irrelevant faults I will drop, highly occurring FD transitions I will keep, and so forth. So therefore partial replication based online testing methodology is now very widely applied for online testing or fault tolerance of embedded systems. Just before I just close down, one thing I should tell you, that this I am not going to elaborate, that without drawing this circuit or finite state machine, how I can find the probability of occurrence or good quality of FD transition. Similarly, there are symbolic models to compute this, because what Professor Deka has told you in the verification part is very important. Whenever there is an FSM based operations which are happening in circuit testing verification, there is always a symbolic based counterpart to handle the state space explosion. So therefore you should not go biased by the fact that partial replication based online testing always requires a FSM model. No, I have shown this in FSM model for illustration to you, so that you understand the concept, but in reality always will be use the symbolic methods. Last but not the least, somebody had tried to use BIST for online testing. What is the idea? This is simple BIST architecture I have explained so many times in the last few lectures, I am not going to go over again, but a very important line here is called the cut is ideal. That what is BIST? BIST is always applied when the circuit is starting up. So you know that there is a normal input and there is a test pattern generator and there is a mask. So when you want to apply the BIST, so this input will be cut and the circuit tester input will be going from the LFSR or some pattern generator, and you are going to do it. Elaborate add details when we are discussing BIST. But now it is in an online testing mode. So in online testing mode, you cannot stop this. You cannot stop. No, you cannot make it stop, because inputs are already coming and the circuit is operating. So if you stop the inputs, this no longer remains an online test. But some scientists have thought that it is not always that all your circuit modules are operating. They sometimes call ideal modules of circuit. But with the parallelism and pipelining coming into picture, the ideal cycles of circuits are very less. But in generally, you know that all parts of the circuit may not operate at all possible time. Sometimes some circuit may be operating and some may be at sleep mode. So there is some important line they have brought it out as the output called circuit is ideal. If the circuit is ideal for some amount of time, because the other parts of the circuits are working, in that case you can stop the normal input and apply the BIST. So this is called actually online BIST. Online BIST and offline BIST is very similar. In offline BIST, the circuit is not started its operation, so you just give the inputs from the test pattern generator and check whether the circuit is normal or not. Standard BIST. Online BIST is same like offline BIST, but just you have to find out whether the circuit is ideal for some amount of time. Whenever it is ideal, you just stop the normal input and do the BIST. That is basically online BIST. But this is not very popular. This was initially it was very popular, because you can basically use the normal BIST to do online both offline. So it was very good and very well appreciated. But nowadays basically this popularity is going down, because basically it totally depends on the ideal time. If the circuit time ideal time is very less, you cannot even test the circuit properly, because only when the circuit is ideal you can apply the BIST, because the online test you cannot stop the inputs. Input can be stopped only when if the circuit is ideal by its own nature, that is given an application, the application is running, but for certain time the circuit is not doing some work. I am not stopping the normal inputs to come, but because of the application which is running, it is idle for some amount of, quickly you do the BIST during that time. So it is totally depending on the ideal time, and therefore if the ideal time is very less, the BIST will not be very successful. And why its popularity is going down very much nowadays? Because nowadays parallelism and pipelining are in picture. They always try to bring down the ideal time of the circuits for high efficiency. So therefore online BIST is not a very popular technique nowadays for all applications mainly. Generally if you have designed a very peculiar circuit where there will be a lot of ideal times, then they can apply this. So as of now, basically this is summary of the online testing schemes. So we have seen first this signature monitoring in FSMs is an intrusive methodology, and also the state explosion problem. Then we have seen the basically error detecting codes. The good advantage of error detecting codes is the area is very low, but again it's a very intrusive design. You have to change the circuit entirely. So therefore people started looking at duplication based online testing scheme. But the problem is, if you go for a pure duplication, the area over it is more than 100%. So if you go for a partial replication, then you should have a prior knowledge of the input patterns, etc. Online based is a very good solution, but problem is that idle times are required, but in modern days, due to parallelism and pipelining, idle times are not there. By comparing it, you can find out that duplication scheme is one of the best and most widely accepted scheme, because again the area of overhead is very high. If you are going for a full duplication, people are not going for full duplication. They basically reduce the area overhead by dropping lot of error detecting transitions, but what they will drop, how they will drop basically is totally in the control of the test engineer. So he makes a good look and survey of the circuit, and that gives him more power to control the test patterns for the testing, and it trade-offs basically, that is lowering the FD transitions in the tester design is more test oriented. So therefore, among all the methods we have discussed, as of now duplication scheme is most widely accepted in a general sense, because it is not 100% duplication, it is partial duplication. And what is partial? That is, which faults he will take, which test patterns will take, which is totally in the control of the test engineer. So therefore, he makes a good survey of the circuit topology, good study on the input applications, and he makes a very nice duplication circuit for you, which is very efficient in testing your circuit. So with this basically we come to the end of this lecture on online testing of embedded system circuits, and we have in this 2 lecture series I have tried to give you a good spectrum of different techniques and what are the advantages and disadvantages. So with this we come to the end of this module, and in the next module we will be trying to look at the basically, because as of now we are mainly talking about hardware, which is basically ASIC, that is basically application specific ICs. But nowadays lot of embedded systems will be developed in FPGAs. So the next module will be trying to look more from the perspective of software hardware combined testing, and mainly which is applicable for programmable devices. Thank you.